The moment humanity first imagined black holes, they were not merely astronomical objects, but philosophical wounds in our understanding of reality. A black hole is born when gravity overwhelms all opposing forces, collapsing matter into a region so dense that space-time itself curves inward. From a distance, it appears calm, silent, and almost elegant. Yet beneath this simplicity lies a profound challenge to the most trusted laws of physics. The question is not only what black holes are, but what they do to the very idea of information, memory, and history in the universe. Information, in physics, is not just data written in books or stored in computers. It is the complete description of a physical system, down to the position and momentum of every particle, the quantum states that define how matter and energy behave. Information tells the universe how to evolve from one moment to the next. In quantum mechanics, information is sacred. It cannot be destroyed, only transformed. If information were truly lost, the future could not be predicted even in principle, and the universe would become fundamentally inconsistent. General relativity, Einstein's theory of gravity, paints a very different picture when black holes enter the scene. According to classical relativity, once matter crosses the event horizon, it is permanently hidden from the outside universe. No signal, no particle, no message can escape. Everything that falls and becomes part of the black hole, contributing only to its mass, spin, and charge. All other details vanish from view, erased behind a boundary that cannot be crossed in reverse. At first glance, this seems like a simple limitation of observation rather than a true destruction of information. After all, just because we cannot see something does not mean it no longer exists. The problem becomes unavoidable when we consider that black holes are not eternal. They slowly lose mass through a quantum process known as Hawking radiation. Over unimaginable timescales, a black hole can evaporate completely, leaving behind nothing but faint radiation drifting through space. Hawking radiation appears thermal and random. It does not seem to depend on what fell into the black hole in the first place. A black hole formed from a star, a library of books, or an entire civilization would radiate in almost the same way. If the black hole eventually disappears, and the radiation carries no detailed memory of its contents, then the information seems truly gone. This is the heart of the black hole information paradox. This paradox shook physics because it forces a confrontation between two pillars of modern science. Quantum mechanics demands that information is conserved. General relativity appears to allow information to be hidden and then erased. Both theories are extraordinarily successful in their domains. Yet when black holes are involved, they give contradictory answers. Resolving this conflict is not a technical detail, but a requirement for a consistent description of the universe. Stephen Hawking himself initially argued that information really was lost in black holes. For decades, this view sparked intense debate. If Hawking were correct, quantum mechanics would need to be modified. Probabilities would replace certainties even at the most fundamental level. The universe would not merely be unpredictable in practice, but unpredictable in principle. Many physicists found this conclusion deeply unsettling. As research progressed, cracks began to appear in the idea of information destruction. Physicists realized that allowing information loss leads to serious mathematical inconsistencies. Quantum states evolving into mixed, thermal states without a reversible process break the rules that make quantum theory work. Energy, conservation, unitarity, and even causality come under threat. The cost of accepting information loss seemed too high. Gradually, the majority of the physics community shifted toward a different belief. Black holes must somehow preserve information, even if the mechanism is subtle, indirect, or extremely difficult to detect. The paradox, then, is not whether information survives, but how it does so without violating the apparent behavior of black holes and Hawking radiation. One of the most radical ideas to emerge from this struggle is the holographic principle. This concept suggests that all the information contained within a volume of space can be represented on its boundary. In the case of a black hole, this boundary is the event horizon. Rather than information falling into a hidden interior, it may be stored on the surface itself, encoded in microscopic degrees of freedom we do not yet fully understand. The holographic principle turns our intuition inside out. We're accustomed to thinking of information as existing within space. Holography suggests that the true description of a region may live on its edges. For black holes, this means the event horizon is not an empty geometric surface, but a densely packed repository of information, with each tiny area contributing a finite amount. The entropy of a black hole supports this idea. Physicists discovered that a black hole's entropy is proportional not to its volume, but to the area of its event horizon. Entropy is a measure of information. This surprising relationship hints that the information content of a black hole scales with its surface, reinforcing the notion that information is stored at the boundary rather than lost inside. If information is encoded on the event horizon, Hawking radiation may not be truly random after all. The radiation could carry subtle correlations that, when considered over the entire lifetime of the black hole, reconstruct the information that fell in. To any short-term observer, the radiation looks thermal and meaningless. Only in the complete pattern does the information reveal itself. This idea challenges our understanding of randomness. A process can appear random while still being perfectly deterministic at a deeper level. Just as shuffled letters from a burned book seem meaningless, the information still exists in principle, scattered among the ashes. Recovering it may be practically impossible, but impossibility in practice is not the same as impossibility in theory. Another approach to resolving the paradox is black hole complementarity. According to this idea, different observers experience different but equally valid realities. To an observer falling into a black hole, nothing special happens at the event horizon. Information passes smoothly inward. To an observer far away, information never truly enters the black hole, but remains encoded on the horizon and is eventually re-emitted. Complementarity avoids contradictions by insisting that no single observer can see both descriptions at once. The falling observer cannot communicate what they see back outside. The distant observer never witnesses information crossing the horizon. Both perspectives are internally consistent, and no experiment can compare them directly. Reality, in this view, depends on the frame of observation. Despite its elegance, complementarity raised new questions. If information is both inside and outside the black hole, does this violate the no-cloning principle of quantum mechanics, which forbids copying quantum information? The theory survives only because no observer can access both copies. Still, this delicate balance leaves many physicists uneasy. As the debate deepened, new problems emerged. One of the most famous is the firewall paradox. Some calculations suggest that preserving information requires the event horizon to be a violent, energetic region rather than a smooth boundary. In this scenario, anything falling in will be destroyed instantly by a wall of high-energy particles. Firewalls directly contradict general relativity, which predicts that crossing the event horizon of a large black hole should be uneventful. An astronaut would notice nothing unusual at that moment. The idea that the horizon could instead be lethal shakes the foundation of space-time geometry and challenges the equivalence principle. The firewall debate exposed how incomplete our understanding still is. Each proposed solution to the information paradox seems to sacrifice something cherished. Either space-time, smoothness, quantum purity, or locality must give way. The universe appears to demand a deeper theory that unifies gravity and quantum mechanics in a way we have not yet achieved. What becomes clear is that black holes are not just objects in space. They are testing grounds for the ultimate laws of nature. They force us to confront the meaning of information, the role of observation, and the limits of knowledge. Whether information is stored on horizons, released through radiation, or encoded in ways we cannot yet describe, it does not simply vanish. By the end of this first stage of the journey, one conclusion stands firm. The universe does not forget easily. If information were truly destroyed, reality itself would unravel. The persistence of the information paradox is not a sign of failure, but a sign that we are close to something profound. Black holes are not erasers of existence. They are mirrors reflecting the unfinished story of physics back at us. To move deeper into the question of whether black holes delete or store information, it is necessary to rethink what is meant by storage in a universe governed by relativity and quantum mechanics. Information does not need a physical container like a box or a disk. It can be distributed across fields, correlations, and quantum states that span vast regions of space. In this sense, a black hole may not store information in a familiar way, but in a form that is radically alien to everyday experience. Quantum entanglement plays a central role in modern attempts to resolve the paradox. When particles become entangled, their properties are linked regardless of distance. Information about one particle is inseparable from the other. Near a black hole, entanglement connects the interior, the event horizon, and the outgoing Hawking radiation in complex ways that challenge classical intuition. Early descriptions of Hawking radiation treated each emitted particle as independent. Later work revealed that this assumption was too simplistic. Hawking radiation is entangled with the black hole itself. As the black hole emits more radiation, the pattern of entanglement must change. At some point, known as the page time, information begins to flow out more efficiently than it flows in. The page curve describes how the entropy of Hawking radiation changes during a black hole's lifetime. Initially, entropy increases as radiation appears random. After the page time, entropy decreases, implying that radiation is becoming more structured and information-rich. This behavior aligns with information preservation and strongly suggests that black holes do not destroy information. This insight reshaped the conversation. If Hawking radiation eventually carries information, then black holes act less like incinerators and more like extremely slow processors. They absorb matter, scramble its information beyond recognition, and then release it in a highly encoded form. The timescale for this process is so vast that it borders on the unimaginable. Scrambling is a key concept here. A system that scrambles information quickly spreads it across all available degrees of freedom. Black holes are believed to be the fastest scramblers in nature. Information falling in is rapidly mixed with the black hole's existing information, making it effectively irretrievable in practice, even if it remains present in principle. This distinction between theoretical reversibility and practical impossibility is crucial. Physics allows information to survive, but recovering it would require decoding correlations across an enormous amount of radiation with perfect precision. For all practical purposes, the information might as well be lost, yet the laws of nature remain intact. Another perspective comes from quantum gravity models that treat space-time itself as emergent. In these views, space and time are not fundamental but arise from deeper quantum relationships. Black holes then represent extreme rearrangements of these relationships rather than literal holes in space. Information is redistributed, not destroyed. The idea that space-time geometry emerges from entanglement has gained traction in recent years. In this framework, the interior of a black hole is encoded in the entanglement structure of the quantum fields outside it. The boundary between inside and outside becomes less absolute, blurring the meaning of loss. If the interior is encoded externally, then the disappearance of a black hole does not imply the disappearance of its contents. Instead, the information transitions from one form of encoding to another. Evaporation becomes a transformation, not an erasure. This viewpoint preserves both quantum mechanics and causality. AD-CFT correspondence provides one of the strongest pieces of evidence for this idea. In this theoretical framework, a gravitational system with black holes is equivalent to a quantum theory without gravity on a lower dimensional boundary. In the boundary theory, Information is manifestly preserved, implying that it must also be preserved in the gravitational description. Although our universe is not exactly described by space, the lesson is powerful. Gravity and quantum mechanics can coexist in a consistent, information-preserving way. Black holes, in this context, are not paradoxes but intricate translations between equivalent descriptions of reality. This duality suggests that information about everything that falls into a black hole is never truly hidden. It is encoded in subtle correlations, accessible in principle from outside the black hole. The difficulty lies not in existence, but in extraction. Nature allows the information to survive, but makes it almost impossible to decode. The role of time in this story is equally strange. From the perspective of a distant observer, infalling matter appears to slow down as it approaches the event horizon, never quite crossing it. Information seems to smear across the horizon and freeze in place. From the infalling observer's perspective, crossing the horizon happens in finite time. This dual experience reinforces the idea that information is not simply swallowed whole. It lingers at the boundary, stretched and redshifted, contributing to the black hole's informational structure. The paradox emerges because we attempt to apply a single narrative to fundamentally observer-dependent phenomena. As evaporation progresses, the black hole shrinks, and the stored information must be released. The radiation emitted late in the black hole's life is predicted to be highly correlated with early radiation. Together, they form a complete record, albeit one that is practically unreadable without godlike computational power. The sheer computational complexity involved introduces another layer of protection. Even if information is preserved, decoding it may require more resources than the universe can provide. This raises deep questions about the relationship between physics and computation, and whether information that cannot be decoded is meaningfully different from information that is lost. Some physicists argue that complexity itself plays the role of a cosmic sensor. Information is safe not because it is hidden behind a wall, but because it is buried under an avalanche of complexity. Black holes become guardians of information through scrambling rather than destruction. This view reframes the paradox in human terms. The universe may be fully deterministic and information-preserving, yet still appear chaotic and irreversible to beings with limited capacities. Black holes amplify this gap between what is possible in principle and what is achievable in practice. As theories grow more abstract, the emotional impact of the paradox remains. The idea that the universe might forget its own past is unsettling. Equally unsettling is the realization that the universe may remember everything, yet in a language forever beyond our understanding. The story of black hole information is therefore not just about physics. It is about knowledge, memory, and the limits of comprehension. Black holes confront us with the possibility that reality is consistent and complete, but not transparent. Truth may exist without being accessible. By this stage, the balance of evidence strongly favors information preservation. The remaining challenge is not whether information survives, but how space-time, gravity, and quantum mechanics cooperate to make that survival possible. The answer likely lies in a deeper theory that has yet to be written. As the discussion moves forward, it becomes clear that the black hole information problem is not isolated to exotic corners of astrophysics. It reaches into the heart of how cause and effect operate in the universe. In everyday experience, causes precede effects in a predictable chain. Information about the cause is carried into the future by physical processes. If black holes were to sever this chain, they would represent a breakdown in the continuity of reality itself. One reason physicists resist true information loss is that it undermines predictability. Even probabilistic predictability depends on underlying consistency. If identical initial states could evolve into fundamentally different final states because information was erased, then physics would lose its explanatory power. Black holes would not just hide information, they would inject randomness into the universe at a fundamental level. This concern has led researchers to explore whether the apparent loss of information is an illusion created by incomplete descriptions. When a system is described only in part, ignoring correlations with inaccessible regions, it can appear to lose information. In reality, the information may still exist in the full system, distributed in ways that are difficult to track. In quantum mechanics, this phenomenon is familiar. When a system becomes entangled with its environment, its individual behavior appears random even though the combined system evolves deterministically. Black holes may simply represent the most extreme example of this process, where the environment includes space-time itself. From this perspective, the event horizon is not a destroyer, but a divider. It separates regions of space-time and limits which correlations are accessible to which observers. Information that crosses the horizon is not annihilated. It becomes entangled with degrees of freedom beyond observational reach. The boundary-like nature of horizons suggests that information paradoxes may arise whenever horizons exist, not just around black holes. Cosmological horizons, such as those associated with the expansion of the universe, also limit observation. Yet few physicists believe that information is destroyed by cosmic expansion. This analogy strengthens the case that horizons conceal rather than erase. The discomfort comes from black hole evaporation, where the horizon eventually disappears. If the boundary dissolves, where does the hidden information go? This question drives much of the modern research into quantum gravity. Some proposals suggest that information is released gradually throughout evaporation, not stored until the final moments. Others propose a dramatic release near the end. The exact timeline remains uncertain, but the page curve strongly constrains viable possibilities, favoring smooth and consistent release over catastrophic events. The final stages of evaporation remain particularly mysterious. As the black hole shrinks to microscopic scales, quantum gravity effects dominate. Classical spacetime may no longer exist in any familiar sense. In this regime, asking where information is stored may be the wrong question entirely. Rather than residing in space, information may exist in pre-spacetime structures. The evaporation process could represent a transition between different phases of reality, much like a change of state in matter. Information would persist through the transition, even if its representation changes completely. These ideas hint that black holes are windows into the architecture of reality. They force physicists to confront the possibility that space, time, and gravity are emergent phenomena. Information, rather than matter or geometry, may be the most fundamental element of the universe. This shift in perspective aligns with developments in quantum information theory. Concepts like entropy, entanglement, and complexity are no longer abstract mathematical tools. They are becoming central to how physicists describe the structure of the universe itself. The black hole paradox has also influenced how scientists think about entropy and time. Entropy is often associated with disorder and the arrow of time. If black holes preserve information while massively increasing entropy, then disorder does not imply destruction. Time's arrow may be tied to accessibility rather than existence. This interpretation offers a subtle but powerful resolution. Information exists, but becomes increasingly difficult to access as entropy grows. Black holes accelerate this process to its extreme limit, creating systems where information is preserved yet practically irretrievable. In this light, black holes resemble memory vaults with keys that are computationally and physically unattainable. They do not forget, but they do not easily reveal. The universe remains consistent, even if opaque. The emotional resonance of this idea should not be underestimated. Humans fear oblivion, the idea that experiences and histories might vanish without trace. The suggestion that the universe preserves all information, even in its darkest regions, offers a strange kind of comfort. At the same time, this preservation is impersonal. The universe does not remember in a way that cares or reflects. Information survives as correlations and quantum states, not as narratives or meanings. Memory exists without awareness. As theories converge on information preservation, experimental confirmation remains elusive. Black holes are distant and slow to evolve. Directly observing Hawking radiation or its correlations is beyond current technology. The paradox is resolved largely through theoretical consistency rather than empirical proof. This reliance on theory has sparked philosophical debate about the nature of scientific knowledge. When direct tests are impossible, consistency, elegance, and unification become guiding principles. The information paradox is a proving ground for these criteria. Despite uncertainty, the direction is clear. Very few physicists now believe that black holes truly delete information. The debate has shifted from whether information survives to how it is encoded, transformed, and eventually released. What remains unresolved is the experience of infalling observers. Does information pass smoothly into the black hole interior, or is our classical picture misleading? The answer may depend on the final theory of quantum gravity, which is yet to be completed. The paradox endures not because it resists solution, but because it demands a deeper language. Black holes are not anomalies. They are signposts pointing toward a more complete understanding of reality, where information, geometry, and time are woven into a single fabric. As attention turns toward the lived experience of observers, the black hole information question becomes even more subtle. Physics does not merely describe objects, but experiences, measurements, and frames of reference. A theory that preserves information must also explain how different. Observers can describe events consistently, even when their experiences diverge radically near a black hole. For an observer falling toward a black hole, the laws of general relativity predict nothing extraordinary at the event horizon, provided the black hole is sufficiently large. Tidal forces are mild, and local physics behaves normally. Information carried by the observer continues inward as part of their natural evolution through space-time. From the perspective of a distant observer, the same process looks dramatically different. The infalling observer appears to slow down, redshift, and fade as they approach the horizon. Their information seems to spread across the surface of the black hole rather than passing through it. Both descriptions are correct within their respective frames. This duality challenges the notion of a single, objective narrative. Physics allows multiple valid descriptions as long as they do not lead to contradictions in observable predictions. The information paradox arises when we try to combine these perspectives into a single story that no observer can actually witness. Black hole complementarity attempts to resolve this by asserting that no observer ever sees information both inside and outside the black hole. The infalling observer cannot communicate back, and the distant observer never witnesses horizon crossing. Information is never duplicated in any measurable way. However, complementarity relies on assumptions about the smoothness of space-time and the behavior of quantum information that may not hold in all regimes. As evaporation proceeds and the black hole shrinks, the neat separation between observers becomes harder to maintain. This tension becomes acute when considering late-stage evaporation. If information is being released in Hawking radiation, then late radiation must be entangled with early radiation. At the same time, quantum mechanics limits how entanglement can be shared. These constraints lead directly to the firewall paradox. The firewall proposal suggests that to preserve information, the event horizon must break down, destroying the smooth spacetime predicted by general relativity. An infalling observer would encounter intense energy at the horizon, violating the equivalence principle that underpins Einstein's theory. Many physicists view firewalls as a sign that something else is wrong with our assumptions. Rather than abandoning smooth horizons, they search for deeper mechanisms that allow information preservation without violent consequences for infalling observers. One alternative is that space-time connectivity changes subtly as information is transferred. Quantum wormholes, or non-classical connections between regions, may play a role. These connections do not allow travel or communication, but may encode correlations that preserve information consistency. Recent work has suggested surprising links between entanglement and space-time geometry. In some models, entangled systems are connected by geometric structures resembling wormholes. This idea hints that information transfer does not require signals crossing the horizon in the classical sense. If such connections exist, they could allow information to be preserved without violating locality or causality. The black hole interior might be encoded in correlations rather than in a separate region of space. Evaporation would then correspond to a gradual reorganization of these correlations. These ideas remain speculative, but they demonstrate how the information paradox is driving innovation. Black holes are forcing physicists to explore radical possibilities about the nature of space-time, suggesting that what we perceive as geometry may emerge from deeper quantum relationships. The notion that space is emergent rather than fundamental reshapes the paradox entirely. If there is no absolute interior region, then the question of information falling in loses its traditional meaning. Information is never inside or outside. In a classical sense, it is simply distributed. Another promising direction involves quantum error correction. Some theories describe space-time as a code that protects information against loss. In this picture, the black hole interior is redundantly encoded in many degrees of freedom outside, making it resilient to disturbances. This coding perspective explains how information can be both hidden and recoverable. Errors introduced by Hawking radiation do not destroy information, but redistribute it across the system. Only by accessing a sufficiently large portion of the radiation could reconstruction occur. Such frameworks blur the line between storage and processing. Black holes do not merely hold information. They actively transform and protect it through the structure of space-time itself. Gravity becomes an information-theoretic phenomenon. While these ideas are mathematically rich, they also carry philosophical weight. They suggest that the universe is not built from particles and fields alone, but from relationships and correlations. Information is not something contained in the universe. It may be what the universe is made of. This shift reframes the original question. Black holes do not delete information because deletion may not be a meaningful concept at the deepest level. Information persists because reality itself is informational. As the debate evolves, one lesson stands out. Every attempt to erase information leads to contradictions. Every successful framework preserves it in some form. Black holes appear destructive only because they challenge human intuition about storage, access, and time. By the end of this phase of understanding, black holes emerge not as cosmic graves, but as transformative regions. They take familiar forms of information and convert them into structures that stretch across horizons, correlations, and timescales far beyond human experience. As the narrative deepens, it becomes clear that black holes force physics to confront not only what exists, but what can be known. Information preservation does not guarantee information accessibility. The universe may obey perfect bookkeeping while remaining fundamentally opaque to observers embedded within it. This gap between what exists and what can be accessed reshapes how loss is interpreted. When information disappears behind a horizon or dissolves into correlations beyond recovery, it feels lost. Yet from the perspective of physical law, it remains part of the total quantum state of the universe. Human intuition equates loss with disappearance. Physics equates loss with irreversibility. These are not the same. Black holes exploit this difference to an extreme degree, pushing systems into regimes where reversibility exists only in theory, never in practice. The arrow of time plays a crucial role in this confusion. Entropy increases, complexity grows, and systems become harder to reverse. Black holes represent entropy maximized within a region, making them the most asymmetric systems in time we know. Yet entropy increase does not imply erasure. It implies dispersion. Information spreads into ever finer correlations. Reversing this spread is allowed by the laws of physics, but forbidden by practical limits. Black holes amplify this disparity beyond any other known system. This understanding resolves much of the emotional tension around the paradox. The universe is not careless with its history. It is simply indifferent to whether that history can be reconstructed by beings like us. The long lifetime of black holes reinforces this view. Information can remain locked away for timescales longer than the age of stars, galaxies, or even proton decay. Preservation does not mean relevance. Information can survive long after its context has vanished. When the black hole finally evaporates, the information does not return as memory or structure. It returns as correlations buried in radiation spread across the cosmos. Nothing recognizable remains, yet nothing fundamental has been lost. This forces a redefinition of storage. Storage does not require stability, coherence, or meaning. It requires only consistency in physical evolution. By that standard, the universe stores everything it ever produces. Black holes then become archivists without intention. They accept information, scramble it, delay its release, and finally disperse it. No record is kept in a readable form. No narrative survives. Only quantum correlations persist. This conclusion unsettles many because it strips information of significance. Preservation without accessibility feels hollow. Yet physics has never promised meaning, only consistency. Black holes obey that promise with ruthless precision. Attempts to restore meaning often involve consciousness or observers, but black holes operate independently of observation. Information is preserved whether or not anyone is there to witness it. Reality does not depend on being seen. This realization echoes earlier shifts in science. The Earth is not the center. Time is not absolute. Space is not rigid. Now meaning itself is not guaranteed. Black holes remind us that the universe is under no obligation to align with human values. From a theoretical standpoint, the information paradox has already achieved something remarkable. It has unified disparate fields such as thermodynamics, quantum theory, gravity, and information science into a single conversation. Few problems have exerted such creative pressure on physics. Entire frameworks have emerged to address it. Even if the final theory remains unknown, the progress made in pursuit of consistency has reshaped modern understanding. As of now, no experimental result contradicts information preservation. Every consistent mathematical framework demands it. Information loss remains a theoretical outlier, increasingly difficult to defend. This does not mean the problem is solved. It means the direction is constrained. Any future theory of quantum gravity must explain how information survives black hole formation and evaporation without contradiction. The paradox therefore acts as a filter. It eliminates theories that allow erasure and favors those that preserve structure beneath apparent chaos. In this way, black holes guide physics forward by refusing simple answers. Ultimately, the question of deletion versus storage dissolves. Black holes do neither in the conventional sense. They transform information into forms that challenge the limits of comprehension, storage, and retrieval. The universe does not run on files or memories. It runs on evolution. Information is not something kept. It is something that happens. Black holes participate in that process without exception. Seen this way, black holes are not anomalies. They are confirmations. They confirm that the universe respects its own rules even under the most extreme conditions imaginable. What remains is not fear of loss, but awe at scale. The scale of compression, the scale of delay, the scale of scrambling. Black holes operate on levels far removed from everyday intuition. As this part closes, one truth stands firm. Black holes do not delete information. They challenge our definitions until deletion no longer makes sense as a concept. At the end, it is concluded that black holes do not erase information. They transform it beyond recognition. What appears lost is only hidden within extreme complexity and quantum correlations. The universe preserves its history even when no observer can recover it. Information survives not as memory or meaning, but as physical consistency. Black holes are not destroyers of reality, but guardians of its deepest laws.